here. This is tour stop number 6 out of 11. We are here at Sandia, wonderful place. Weather's great outside. We've got the Brain Trust from Sandia here. So why don't you please introduce yourselves and tell us what you do.
Hi, I'm Craig Vineyard. I'm a research scientist, and I explore computing technologies for a range of applications, scientific computing to remote sensing with emphasis in machine learning and neuromorphic computing.
Neuromorphic. Nice. Okay, good job. Now you've got to top that.
Okay. So I'm Rob Hoekstra. I'm the senior manager for the Extreme Scale Computing Group here at Sandia National Labs, and we're a part of the Center for Computing Research.
Okay, senior manager and advanced scale. That does kind of top you a little bit. So, okay, next up.
I can't top that. I'm Sivaraj Manikam. I'm a researcher here at Center for Computing Research. I work mostly on HPC, primarily in the intersection of modeling and simulation, and on machine learning for science applications.
Well, you're hitting on all cylinders there.
Oh,
excellent. Okay.
I'm James Laros. I'm a distinguished staff member here at Sandia, computer architect. I lead a number of our advanced technology programs here at Sandia that we'll probably be talking about today.
Excellent. Excellent. Well, let's just kick off, and whoever wants to take this can take it. What's the real mission here at Sandia?
So I would say, Sandia, we define ourselves as a multi-mission laboratory. Of course, primarily we are a nuclear deterrence laboratory run by the National Nuclear Security Agency. But beyond that, we play very significant roles in energy and water security, with the Department of Defense and the intelligence agency. So we have a very broad range of mission work. So.
And what kind of computing resources are we now deploying against those missions?
So it's a very wide variety. I would say currently we're still in what I would call the traditional computing space. High performance computing clusters and infrastructure still dominates a lot of what we're deploying, although you'll see more and more GPU accelerated nodes are becoming more and more dominant in our space. Beyond that, as we go forward, what you'll hear in some of the responses to the question here is looking at emerging computing technologies like quantum and neuromorphic and other what we would consider accelerator technologies that are more narrowly focused on particular mission critical areas and how we can best utilize those technologies to support those missions.
I mean, that was one of the things that surprised me about Sandia a little bit when I came by in 2018, is that you're kind of a test bed for advanced computing.
Yeah, so that's where a lot of what we do, the role that we play is kind of one of our programs, Vanguard program, not surprisingly named because it's a spearhead, is kind of leading the way in testing very advanced technologies and trying to determine if they're feasible to apply to the ASC mission. And our testbed program is another good example of that. That's even a little bit more far out, so we'll kind of test anything we can find with the testbed program. Craig's doing the same thing in neuromorphic. I mean, we really are anywhere from a couple years to at least a decade out and trying to investigate what's next, which is where AI/ML comes in for one of Siva's focuses. So we're really kind of trying to lead the way, trying to do the more risky thing in advance of trying to deploy technologies at other laboratories at larger scale for kind of immediate production use, where ours are not destined for production use right away. So
to me, that also sounds like you take a lot of the risk out of the bets that they have to make on technology at some point.
Yeah, absolutely. The last time you were here, Ken Alvin used a good phrase. We're kind of buying down the risk for the larger, more expensive platforms because it's more appropriate to not invest a couple $100 million on something that's you're not too sure of. Well, it's a little bit more sensible. Taxpayers will appreciate we invest a little bit less money on the really risky things to see if they're going to work out.
Very good. Very
As
good.
Jim mentioned a moment ago, as part of that risk reduction, uncertainty reduction, I lead a lab called the Neural Exploration and Research Lab, which by design is exploring a breadth of emerging computing architectures. And part of that effort is exploring and understanding, as these new paradigms of compute inspired by the brain come out, how do they scale? What missions do they support? Are they going to be something that's going to scale up to address scientific computing codes? Are they going to be a low size, weight, and power solution that might go on a drone or a satellite or an extremely low powered edge sensor? And what are the computational complexities associated with the algorithm architecture interplay?
Are you seeing some promise there?
We're seeing a lot of potential, both in terms of near-term technologies as well as looking at down the road. So we see both wins now using existing technologies, but we also see a lot of innovation worldwide in terms of new materials, new devices, new technologies, hybrid future solutions.
Well, actually, that kind of leads, the word hybrid leads into my next question. Are you using public clouds at all?
So to a limited degree, right? So one challenge with public clouds is if they're well suited to our mission needs in terms of data security and such. But also there's a cost function there too. Is it economical for us or not? And you've probably heard this from many others. Right now, we would tend to say if you have high usage of a platform, you're probably better off buying it and putting it on-prem as long as you have the support resources. Where cloud is really valuable is, of course, is in the much more elastic regime of, we're drastically changing our workloads and our use over time, and we need to we have big fluctuations in kind of our needs for computing resources. So right now, I would say a lot of the labs, including us, are probably more on the end of still using a lot of on-prem resources at very high utilization levels.
Yeah, and that's why that probably won't change.
So what I think you'll see more and more of going forward, and we're certainly aggressively pushing in this area, is on-prem cloud resources. We see a great degree of value in the infrastructure, both hardware and software. For cloud, it can be much higher availability, much higher usability maybe than traditional computing resources, and certainly many of our mission areas could benefit from that. But I think for many of us, we expect that infrastructure to primarily be on-prem, but we're also looking at whether or not we can then grow that and extend that to off-prem resources as well in the future.
That said, we are heavily leveraging cloud technologies.
Yes.
So we're looking into workflow orchestration software. Containers is something that all three laboratories are very focused on for a number of reasons: repeatability, provenance,
portability.
Exactly.
Yeah.
So that's something that all three labs are really grabbing a hold of. But the workflow orchestration, leveraging cloud technologies, even for cluster management, is something that is being heavily exploited. But as Rob said, we're going to have to probably kind of transition slowly, if no other reason, the security aspect of it for doing cloud technologies.
That makes
And
sense.
I'll state one of our very best examples at Sandia right now is a lab level push for digital engineering to support primarily the nuclear deterrence area, but also other missions too. And we see cloud infrastructure as an obvious way to better support that digital engineering mission. And what we're really hoping for, and that our organization is really exploring, is that seamless integration from the desktop all the way up to the largest supercomputers. How can we give our users, our analysts in the different mission areas a very seamless experience to take advantage of those resources going forward. So
That's the tough part, unless you're going to start writing your own schedulers and things like that, which you could do, right? Let's jump on to machine learning. I want to get you in the conversation.
Happy to do that.
So what about machine learning? Using it? You're using it. I mean, in 2018, I think we talked about it a little bit, and it was early.
It's not early anymore. We are using machine learning, and at different levels. You can think of it. Whether we use machine learning right in production application is debatable. But we are starting to use it even for some selected production applications. Material science is one example where we are already starting to use machine learning quite a bit because they adopted the technology very early because the simulations were already very, very expensive. Right? So now you can build surrogate models for very expensive portions of the simulations and deploy them on hardware that are conventional or accelerator-based or only focused on machine learning accelerators. Right? Like there are a lot of machine learning focused accelerators that are coming, and we are evaluating those accelerators for machine learning workloads.
I think one of the last time I looked, and it was a while back, there were 50 different startups and big companies.
Exactly,
Yeah.
exactly. This is a field where it's getting crowded very quickly. So we talk to all of these companies, as many as we can, evaluate their technologies in our test beds, evaluate some of them in a slightly more, slightly larger programs than just buying a test bed and evaluating it. Once we are confident they are more mature, their programming models are more mature, and then we can actually use it. And then we compare it to traditional accelerators like GPUs,
Sure.
right? So, and that is our primary workhorse for machine learning as of today, actually. All our machine learning workloads, the training portion is very, very expensive, so we use GPU acceleration quite a bit there as well.
Are you using kind of the broad swath of the popular GPUs? I guess I might as well just say NVIDIA and AMD.
Oh, and Intel, right?
And
so
Intel,
so
okay.
we play a big role in the exascale computing program, and what we call ATTM, and within the NNSA, the twin for the exascale computing program for the NNSA labs. So our center plays a big role, and Sandia has a big role in both these programs. And the programs are targeted towards our exascale machines, which are going to be AMD-based machines, but there are pre-exascale ones that are all NVIDIA-based machines.
Yeah.
So portability is a big factor there. And through the exascale computing program, we also have ties with Aurora, which is
Sure.
an Intel-based one. So we support all three in our software stack.
And that's not an easy chore.
No, it's not. It is. So we have invested, thankfully, this is something that we have invested for more than a decade, actually. This is not something that came after the exascale computing program. We started investing in portability somewhere in the 2010s. And COCOS is our primary vehicle to support portability. And then it started just as a programming model. It is no longer a programming model. It is a big ecosystem with numerical libraries, tools, Python support. So there is and that has helped us build our modeling and simulation applications on top, so we can try out any of these architectures. All we have to change is add a COCOS backend, and then we'll be able to support it.
Simple.
Yep. Very simple.
There's a woman at Pacific Northwest National Lab that I interviewed who's working on a universal compiler for all of the various, or as many of the various accelerators as you can get. And primarily starting out in computational chemistry and something else that I forget. It's difficult. It's very hard, and I think that some folks have broken their pick on this before, but she will not be discouraged.
Good.
And you know, the challenge that we're all well aware of is how specialized you make those technologies, those interface layers. Is it more like a domain-specific framework targeted at only computational chemistry, or is it very broad, trying to support the whole community?
Computational chemistry to start,
Yeah.
tomorrow the world. That's good. It's great to see him try.
Our lead of the COCOS project, Christian Trott, would tell you he's trying to take over the world with COCOS, right?
So before you move off the AI/ML thing, something that we're doing I think is really interesting that's NNSA sponsored is our Advanced Memory Technology Program. And the one that we can talk about so far is Cerebrus. And that's an example of where we're taking an established AI/ML technology and looking at, well, can we do our simulation mission on this hardware?
Can you?
And yeah, so I'd like Stephen will speak to detail a little bit about that, but that's one example of a couple that will come that we can't announce yet that should be interesting. And another way we're leveraging and looking really far ahead about what we can do about certain technologies.
Because that's a really interesting architecture and company.
It is.
That is very interesting. So tell us.
Exactly, yeah. So the primary interest, there are two interesting things about this architecture, right? Number one, it is data flow. So you try to minimize memory movement as much as you can and keep the memory on the chip, keep the data on the chip, right? And move the data between different processing elements, let's say. Okay. So that gives you a lot of performance, saves you power. So we are interested in that. The second interesting aspect is sparsity. How you can handle sparsity in this architecture. So they designed it really well, and this is a new announcement, as Jim mentioned, that came along probably a couple of weeks ago as part of our Advanced Memory Technologies program. We're working very closely with them to see if we can take this hardware that is originally designed for machine learning, right, to accelerate machine learning application, but use it for our traditional simulations. What are the changes needed in the hardware, changes needed in programming models, and of course changes needed in algorithms, right? So we will explore the whole suite of things.
Yeah, one additional point is, to me, the value of these programs, I mean, each individual contract is valuable in and of itself for what you're doing in that contract, but to me, overall, at a higher level, these contracts are extremely valuable in establishing a conversation, sometimes with well-established vendors, but in this case, this is a very new vendor. It's very new technology, and we're establishing a conversation with them, and they're going to be learning from us. So what they gain from us and that technology transfer from us to them is one of the most important aspects of what this relationship will be.
And so many relationships.
Exactly. Well, we see some of the previous fast-forward, design-forward programs and the investments in those areas resulting in exascale platforms. And this is the same thing. We're looking down the road and saying, okay, well, we might not have it tomorrow, but in 3, 5, 10 years, we want this to intercept something that can be widely useful for us to satisfy our mission.
Very, very interesting stuff. Speaking of computing technologies and capabilities, there's been a lot of talk around CXL and composability and things like that. To me, as a layman compared to you guys, it makes a lot of sense because applications are lumpy in the types of, in what components they use. And perhaps being able to have network attached compute, for instance, would be able to grab accelerators out from other systems and change those ratios. Is this something, I'm sure it's something you're looking at, but what do you think?
Absolutely, something we're looking at. You hear disaggregated memory, for example, is one of the things that gets discussed very, very heavily with CXL. So I kind of look at CXL as something that's absolutely going to make a big difference for us, but using it to apply to something that it might not be best suited to is what we hear a little bit of that from the vendors. And back to what Siva was saying about data locality. Well, CXL is pretty cool and it can probably do some pretty good bandwidths, but it's not a substitute for tighter integration and much faster. When you were here last, we were talking about changes in memory bandwidth that were on the horizon with HBM.
Yes.
And we talked about, since we're all very old in that case, the last change in memory bandwidth, which was sucking the memory controller into the die. Well, this CXL isn't going to fix that, right?
No.
It's certainly not going to fix the latency characteristics.
No.
But it's kind of like, solid state devices and stuff. They were this huge boom for I/O, and they really changed our workflows and how productive and efficient our applications ran on the machines. CXL is probably going to be one of those things that's going to improve in a bunch of domains, but I don't think it's going to satisfy the acceleration that we were looking for example, from the AMT program. We did have interest from companies proposing CXL-like strategies, and it really wasn't going to give us the 40x improvement that we were looking for in that program.
Is it primarily the latency that we're looking at?
I think it's both. I think it's both latency and you can get some pretty good bandwidths, but you're still looking at it being farther away from
Yeah.
the processing elements, and you're adding probably NUMA effects or orchestration of where your memory is when you want to
There's
use it
gotta be
right
some
then and
overhead in there
there.
to manage
So,
it.
yeah, for a lot of applications, it's going to be fantastic.
There's physics limits like the speed of light, right? That great
Remember a
challenges at some
vendor
point.
About 15 years ago, calling me all excited, hey, we slowed down the speed of light. I said, get back to me when you speed it up, because that's what we're really looking for.
So I would just state at a higher level, I mean, I think this is the dream for our community, not just us, is if we had these standardized interfaces like CXL that would allow us to mix and match different vendors' IP,
Yeah.
at least at the package level. So we could build custom node level solutions for our future systems. I think many of us really would like to see that.
Yeah, later on, it's given things like coherency and
Yeah.
a lot of memory semantics that we don't currently have. So there's definitely advantages.
I think there's definitely something there. I think it's inevitable. But there's always going to be that trade-off between, I don't know how you get the same amount of latency out of making extra hops. You can't. So there's always going to be a trade-off as to whether having, 12 GPUs on one node is a win versus being able to communicate with those GPUs a bit slower. Yeah, we'll see what happens. So speaking of exascales, we have been, when are you going to get yourselves an exascale system?
As I said, our role is more of a future-looking role. So whether or not we're going to house an exascale system, we house petascale systems now, but we weren't the first. So even though we were the first for a teraflop
Yes,
way
you
back
were.
when, we are not on the large system platform rotation for the NNSA. Those systems go to Lawrence Livermore and Los Alamos. So
You've had some big boxes here, though.
we've had in the past, yeah.
Yeah.
And, Red Storm, for example, all
Yeah.
these systems that we see being deployed today at Los Alamos and upcoming in Lawrence Livermore are all, basically they're an evolution of that original architecture that Sandia architected with way back Cray at the time. So, that's another good example of how we were kind of leading innovation in that space, right?
Yeah.
And that impacts, not only did that impact the DOE, that impacted the entire world.
Yes, it
So,
did. Yes,
stuff
it
like
did.
that, that's the sort of impact we want to have.
I mean, that's the value of having a Sandia-like place, is being able to pioneer all of these things and give the unheralded a chance.
Yep.
And that's great.
Well, and I'll follow on by saying I need to give NNSA's ASC program and its leadership credit that Tuk Wong and crew have been pushing us to be better and better collaborators with the other labs. So the 3 NNSA labs, we every year I believe we work more and more closely together. And the future I see is a more unified infrastructure across the labs, where it matters less and less where the hardware sits, where the exascale system sits, or other infrastructure sits, because we all have collective access, common access to that infrastructure, no matter where it sits.
And that's a thread that's run through every interview I've done up until now, is that you're all saying that we will be using, for instance, a piece of Frontier. Now, I hope you've told Oak Ridge that you're all going to be jumping in on that. I assume that that's probably in the email. But yeah, everybody's going to be using those shared resources, and that's great.
Well, within the NNSA space, Crossroads is the next big system up at Los Alamos, and then El Capitan at Lawrence Livermore will be the NNSA's first exascale platform that we'll have access to. So
you're going to be using everybody's. Nice. So how many of you are going to SC22?
I'm going, and I think I was going.
Craig's the only
I'm the only one not going.
You're not going? I'm going to miss you.
It was a poor decision on my part.
Well, a jump ball question for anybody that wants to jump in. Is there anything in particular that you're looking to see or hear from SC22? Or anything in particular you're looking forward to?
For me, I'm actually not going either. For me, it was always the surprise, right? The one that you didn't expect, the one that you didn't know anything about. You're walking along and there's like this tiny little booth with some crazy looking people in the booth.
Yeah.
And they just have this really cool emerging technology that, they've just maybe done a poor job of advertising or whatever.
And then you stop.
And you
then
stop and you
ask-
talk to them.
And then you ask, really?
Yeah, exactly.
No. Really?
Yep,
It does
exactly.
that?
And
Yeah.
chances are, for that very small booth in that emerging startup company, you're talking to the founder, you're talking
Yeah.
to the CTO, you're not talking to somebody that they got somewhere from the company to sit there and field some questions and take notes and get back to you. You're talking to the person that developed the technology. To me, that's the most exciting thing about SC is when you stumble upon that. And unfortunately, it used to be more common in the past,
Yeah.
but now, for good or bad, you kind of know about things sooner with
Yeah.
as easy as it is to advertise things.
But you kind of get when you see something in the news, you kind of get a little bookmark in
Yeah.
your mind. I need to check them out.
Yeah, and it's cool when he can't make it work the first 5 times, but then he gets it to work, and
Yeah.
it's just so much fun, because that's, for Sandia is an engineering laboratory, and most of us are, researchers, but we're still engineers, and, that's fun, right? Breaking it 15 times before you finally get it to work, and that's exciting.
That is very cool.
And I would just say, and that's always been an element at SC. Now it's an even more dominant element, right? I mean, as you pointed out, machine learning, AI, there's, not just tens, but hundreds of startups working in that space, and there's quantum, and so I think that's a much more significant element than historically there was at supercomputing. So.
Yeah, so let me add something. So we talked about Cerebrus earlier, which is this AI startup that we are working with. So I'll add something more on top of that, which is we have this collaboration with this company called Samanova, which is another
Yes.
AI startup. And we have a collaboration with them as part of the ASC's Advanced Machine Learning Program. And we have had this collaboration for a while now, and we have giving you some preview of the supercomputing results. We have some exciting new results on how their hardware does on machine learning workloads that we care about. And we have seen some very interesting results, and I want to see how it gets received in supercomputing.
So an announcement, you're pre-announcing an announcement.
Yeah, I'm hoping this doesn't show up, the interview doesn't come out.
It'll be later this week,
Yes.
so it'll be virtually indistinguishable.
Yeah.
And you didn't really say anything anyway.
Yeah, I
Yeah,
didn't say
the collaboration has been announced. He's
Yeah,
just saying there will be some results
And that's
discussed.
not the first time I've heard Samanova on my
Yeah.
trip around here. Everybody seems to be collaborating with
Yeah.
them to some extent,
So we
which
have
is
a,
good on their part.
Yeah.
Good job for them.
yeah, we have an active collaboration with not just Sandia, with TriLabs, but we have a contract with them as part of Sandia's AML program.
Okay, very good.
Yeah, as another take or another perspective on what they've already said, I find it exciting that as you see the maturation of those collaborations, as you see the field going from AI and ML not being present 5 or so years ago to now being a heavy presence, but there's also a sense of realism to it, that it's not, well, maybe this technology exists, does it exist? But in many cases you can see on the demo floors, here's this real technology that's here today. It's not after
Not
a
a
few
science
miracles.
project.
Yeah, exactly. That it's that helps add realism and shows the timeline of neuromorphic arriving now, of machine learning accelerators arriving now and being able to impact the world
Yeah.
today.
Exactly. Now, as we start to wind down, I've got what I think is a great question. And put yourself in the mindset that you're addressing every vendor in the HPC community. What do you need from them 3 years out? And 3 years is kind of specific because 12 months, 18 months, they can't course correct that much, but 3 years, they can. What do you need? All of you. Doesn't have to be just one item either. Yeah, I knew you had something.
There's a lot of detailed things. I think the most interesting thing that maybe we would like to see in the time frame that you're talking about, and I think we're starting to see this a little bit move in this direction already, is some improvements in manufacturing and packaging that allow us to move towards more heterogeneous architectures that actually work a little bit more seamlessly, right? So, having different nodes with different sort of accelerators hanging off a PCI device, that's one way to get a heterogeneous architecture. It's probably not optimal, right? So if we kind of break down some of these barriers from vendor to vendor, for example, like, well, I'd really like to have this technology from this vendor mixed with this technology from that vendor, but if I want it tightly integrated, forget it, because there's just no way to do that. So being able to...
Let's probe that a little bit. What would you suggest, other than PCI, like a universal socket?
CXL does that for one thing, right? Rob was alluding to the fact that might help with more tight integration. I mean, you're reducing some of your, especially latency characteristics. If you use that for a die-to-die communication, for example, instead of the proprietary die-to-die communications, you've basically taken away most of the problem. I'm going to say most, but you've taken away some of the problems of sharing IP, because the responsibility of one vendor is to interface with CXL. The responsibility of the other vendor is to interface with CXL. And as long as you can get it manufactured and packaged, maybe you can actually accomplish that. And then one thing that hasn't been mentioned here that we're very heavily investigating is RISC-V. So RISC-V is basically completely open.
Yeah.
And again, just like AI and ML a number of years ago, there's this explosion of RISC-V vendors starting to pop up. And
True.
we're speaking to a lot of them, and we're trying to make sure that they pay attention to high performance computing, in addition to some of the other potentially more lucrative spaces like automotive and things like that.
Yeah, I've seen a lot, of course, like everybody, RISC-V, but not that much on the high-end computing side.
Well, exactly, and you could, this doesn't look too different from the last time we spoke, right? We started out in the testbed program investigating ARM.
That's
ARM
right.
was not ready for prime time in HPC. We even started when it was 32-bit, received the first 64-bit processor that was definitely not HPC capable. And that evolved into Astra, which was the first petascale ARM platform. So you can imagine us doing the very same thing with RISC-V if we get appropriate technology partners that can deliver something like this for us.
And I would say Astra was an inspiration for Fugaku.
Yeah, exactly.
You showed it could work.
Yep. And we, the unsung, real important developments there were a lot of the software stack, a lot of compilers, all that other stuff, right? The things that aren't so snazzy, we really filled a lot of gaps there. Well, we need to do the same thing with RISC-V. There's a lot of gaps to be filled there, especially for our challenging workloads. And then you start mixing in all these different types of technologies, it'll probably be a heck of a lot easier to interface AI, ML, neuromorphic, whatever, with a RISC-V chip that isn't protected by a lot of IP rights. You don't have to get, it's even easier than ARM. The last time they were saying, well, ARM opened up things for us, but you still need an engineering architecture license for ARM. You don't need that for RISC-V. So it's even opening the ecosystem up further and allowing more and more vendors to participate. So, and we're aware of a lot of things that we can't speak about publicly that are really encouraging to us about different vendors working together to maybe deliver some of these things that I'm suggesting in the future.
I mean, for some reason, when you were saying that, I'm envisioning a motherboard accelerator socket that's standard. And you need to fit your accelerator into this.
Yeah, it's not too different from OEM, right?
That's not that much. No,
exactly.
Not that much. So vendor wish list, what else?
So I'll give you a use case, and very similar to what Jim was pointing to, but the vision that we have, and it is partly a vision, partly a need actually, right, is to have our modeling simulation running on one side, helping generating data that we can train a machine learning model on simultaneously, and then use the machine learning model in an inference engine, and then come back, generate new training data on a GPU-based modeling and simulation.
Motion machine there.
Well, it's a feedback loop, right?
Yeah.
So, and we don't gain just by having a modeling and simulation hardware or a system for modeling and simulation, or just by having something that is fantastic in training. we need all of these to work together.
And it automatically feeds back
Into
the
it
simulation.
and move the data. Some of it could be offline, say the training, let's say I have the training offline, but still.
Why?
if the-
Why not do it all online? Because I think
Ideally, we
it's
would
possible.
like, exactly, ideally, we would like this to be online, to generate the training data only where I need it, right? I don't need to generate a huge amount of training data and then filter it in order to do the correct amount of training. So this feedback loop requires all sorts of innovation in terms of systems, right? Not
Yeah.
just an AI/ML accelerator, not just something that is for modeling and simulation. And the other thing is, when somebody is developing this, they need to think about how they are going to program this whole thing.
Well, yeah,
So
there will be some programming needed.
Exactly. So personally for me, I always go back to that. It has to be something that science people can program. You don't need a computer science degree in order to program these systems, right? And whatever is going to achieve that is going to be the one that we would like,
That's-
right? Yeah.
That's a big win. You put that sort of thing together. What do you call this?
It's actually nothing different than a heterogeneous system that supports this use case that I talked about.
You're
It
not
is-
thinking big enough. We need to put a name on this. Because this whole feedback loop through that could be the keys to the kingdom in some types of applications and domains.
It is actually getting done in some portions, like very, very small active learning loops. People have implemented this,
Mhm.
right? But it's quite
But
challenging for
scale.
the scale that we are thinking
Yeah.
about, right? If our material simulation is running in an exascale system that we are currently deploying, right, which has AMD-based GPUs, and it is running on a full exascale system, how am I going to take that training data and move to an accelerator that is for training purposes? It is quite a challenge, actually.
Yes.
It's not easy to solve.
It's a beautiful vision, though.
3 years? You said 3?
3 years. We'll get them started on it.
Yeah, no problem.
Well, and I would suggest that these kinds of examples have led to a shift in how our HPC community, the national labs and the vendors, how we discuss our needs going forward. It's not as focused on, can I put a big flop heavy machine on the floor? You know, it is much more around what do our future workloads look like
Yes.
for our mission, for the nation, and what is the overall architecture design of a system that potentially that is very heterogeneous and expands beyond one data center, you know, and may tie into experimental facilities or sensors or other components like that. That's where our conversations are starting to shift with the vendors. Okay, how do we create a solution to those kind of workloads instead of how do we run a flop heavy job in one data center? So
Very good.
So,
Wish list, what do you got?
yeah, I may be just rehashing what Rob said in a less eloquent way, but one of the lessons learned, one of the things I often encourage interactions with vendors is to tell me what their architecture is strong at. If they're changing the paradigm of computing in some way, understandably, they often look to us, to historical workloads, to help say this is what we can do, but I want to see how should we be using your system, not what are you good at, and that's not an easy thing
Don't
to
make them
answer.
find out.
Yeah,
Let me
exactly.
know.
So that way we can co-design that, we can really get big wins, not just incremental advances, but let's really leverage, let's lean into the novelty that they're innovating, let's use their great engineering to its full potential.
I can't believe it took this long for one of us to say co-design, since we feel like we've championed that.
But I mean, the other thing is not just tell me what you're good at, tell me what you're bad at.
Right.
It's not a no-go, but need to know both of those.
Right.
And that's what I try and do in my small way when I'm getting pitched by new companies, is that, you know, we're good for everything. Well, no, you're not. Come on, you're not. What are you best at? What are you worst at?
Right.
You know, that would be helpful. Sue, what excites you about the future of supercomputing? What gets you bouncing out of bed?
Yeah, so I'm biased. This is going to be an obvious answer. Neuromorphic computing. So we are seeing systems right now, hundreds of millions of neurons. In the next year, we're marching towards a billion neuron system. As a rough reference, human brains have, say, 80 billion neurons. So we're revisiting similar questions from traditional HPC. How do you communicate? What do you do with that many neurons, with larger systems?
It ain't open API.
Exactly. What is the software stack? What is interoperability? How do we leverage the unique strengths that neurons fundamentally offer a different paradigm? It's not a matter of trying to use all of them at once, but using the right neurons. It's a different objective, optimization objective. But we're seeing large-scale systems worldwide, from Intel's, from the European Union, out of the Spinnaker effort. Historically, IBM's invested, seeing a bunch of emerging solutions, and we're at a bit of an inflection point where the community's addressing these questions with a more stable software representation, asking questions about scaling. The systems are there, and so I'm really excited to see where it's going. We are showing novel applications. Sandia's led some work looking at doing things that you wouldn't expect with a neuromorphic system. You wouldn't think of just, let me do a traditional neural network, but using it to do a large-scale diffusion random walk, doing scientific codes using neurons as your fundamental compute element, looking at what can I do if I have a computational system that has a lot of little cheap compute cores that have very large, very integrated communication patterns that have preservation of state, that get into the notion of how can I maximally leverage those to do interesting solutions. And so I'm interested to see how far it can push, where we can go.
Very cool.
Well, and I think that's what I'm most excited about. Earlier in my career, I felt like all the solutions were put together commodity parts to a great extent, right? And
it sort of seemed like the end of innovation for a while there.
Exactly.
Yeah.
And what really excites me is these kind of opportunities on the horizon, where while we still may have a significant amount of more conventional parts, we're now seeing technologies like neuromorphic or quantum that may be really strong options for acceleration technologies in our future supercomputing systems. And honestly, earlier in my career, I wasn't sure if that was going to happen or not. And I'm thrilled that now appears. I mean, quantum, of course, may be quite a ways out still, but things like neuromorphic and some of these other custom acceleration technologies, they look like they're going to impact us in the 3 to 5 year time frame.
It's so funny you would say that, because just a few hours ago, Irene Walters was saying much the same thing. At one point in her career, it looked like we were at a dead end, and Moore's Law was dead, and we were at the end of innovation, and look where we are now.
Yeah, I would agree with Irene.
Okay, let me say what I'm interested in, or I'm excited most about, is how HPC has become commonplace. Right? It used to be a niche technology.
Yes.
Where supercomputing was not that big. I mean, it still was a great conference, but it was for this niche group of people who work on this topic, focus on interconnects, focus on improving BLAS and LINPACK performance. Now it is so commonplace. We have teraflops in our pockets. What do we have? If you run LINPACK on our phones, how much we get now. So it is technologies that we thought was only for these very specialized apps is becoming like ubiquitous, right? Everywhere. And some of it is due to machine learning and like how we use machine learning as a society, right? For everything from like adjusting our photos or finding new images and searches or something like that. But some of it is what the hardware industry has done, right? Give us so much power that everybody is able to use HPC now, and I see like it only getting better over the next decade. So very exciting times to be here.
Close us out, Jim.
I have to say the first thought in my mind when you said that was retirement. In honesty, what I'd really like to see is a future that doesn't look anything like our past. And this is a little bit of what Siva said. HPC. Maybe we don't even need the term HPC anymore. I'd love to see the terminology completely change. I'd love to see when you say system or platform, I'd love for us to be able to debate what exactly that word means anymore for a half an hour, because it's more ubiquitous computing. But something that's probably uncommon for a computer architect to say is, I haven't been excited about flops now for 2 decades. I mean, it's really not at all interesting to me. There's some use for those metrics, but what really matters is what we do with these systems, right? What does it make us capable of? And that's what I would really like to see in the future, is just expanding our capabilities rather than measuring, just on a top 500 list what we're able to achieve, percentage of theoretical flops or whatever. What is it that we can do with these future systems? And by putting all these components together, these future technologies that are just emerging, what does it enable us to do? And hopefully we do good, productive things for the nation with those. But I'd really like to come back 3 or 5 years from now and be completely irrelevant, right? I mean, if you just disappear for 3 to 5 years, it's so different that, what you know from history and your experience, that'll always be important. But if things are just so different 3 to 5 years from now, I'd be so pleased about that.
I think you've got a pretty good chance of that coming true. Because if you go back 3 to 5 years, it's changed quite a bit. And that's a great note to stop on. Thank you so much for your time. I really appreciate it. And all the viewers out there will appreciate it too. This was a deep session. We covered a lot of ground and we dove down quite a bit too. Good job. So thanks.
500 miles of open road, and I'm driving down the highway.